Hey friends, Ben again. This is a video to talk about the concept of differentiability. I am trying out a couple of new things here. One is that I'm doing this from my kitchen in the middle of the night, and the lighting's a little weird. There's also dogs in the background, so that might disturb us, but the main thing is that I'm trying out a new tool on the iPad that I'm hoping will let me edit things a little bit easier, a little bit better. We'll see. All right, so the essential concept behind differentiability is that if you have a function whose graph doesn't have any sharp edges on it, then that function at any place on the graph of it will be more or less smooth. And with that smoothness, you are able to put a tangent plane to the surface at some given point. So what we're trying to do is to put that on more firm mathematical ground with a definition. Okay, so let me share my screen with you, assuming that will work, because I've had a little bit of problem with that today. And it looks like it's going to work. Yay. All right. And this is my new tool, and it has a presentation mode. And let's see. I think you don't see the interface. All right. So, yay. All right. So, differentiability. So when we make reference to a function being differentiable, what we're talking about is, and it doesn't have a pointer, well, that is not going to help one damn bit. Yeah, great. All right, so when we talk about this definition of differentiability, then it has an equation associated with it. And the equation, as you can see there, f of x plus delta x, y plus delta y. So if you remember what we did with our partial derivatives the other day, that had just an x plus delta x or just a y plus delta y. So with the differentiability definition, we are in fact going to have both of those going on at once. So the pieces here are that we have f sub x, so the derivative of f with respect to x is going to appear and be multiplied by a change in x. The derivative f sub y will be multiplied by a delta y, and then we're going to have these kind of junk terms here, epsilon 1 delta x and epsilon 2 delta y. And the key to differentiability is that you're going to be able to show that those epsilon 1, epsilon 2 terms go to 0 when delta x and delta y are going to 0, okay? Essentially, if you look back at the stuff we did with Taylor polynomials in one dimension, what we're saying here is that your tangent plane, which is a first degree Taylor polynomial, that the rest of it that goes beyond that, remember we didn't spend a lot of time on it, but the remainder terms are going to be going to 0, but we're doing it higher dimensions and so forth, okay? So again, visually, all this means is that you get a tangent plane and that your surface doesn't really have any sharp edges there, okay? So let's take a look at an example here, and we need to show that this function here, f of xy, actually, let me try to use a different color for that. Okay, so this function here, f of xy, we're going to try to show that it's differentiable. Now I'm going to have problems for you to do as well, but any of the problems that we do on this, we need to be talking about polynomials. The reason is it's just not algebraically feasible to ask you to do this with something that's more complicated. All right. So as mentioned here, for later, we're going to need the f sub x, and you just get that by saying x squared y, that's where the x's are. Take the derivative of the x squared and you get 2x, and times y as a constant. And then your f sub y, you'd say x squared y, take the derivative of y, so you get x squared times 1. And then minus the derivative of y cubed is just 3y squared. Okay? So then we're going to have to write down all this mess of stuff right in here. Okay? And so we have to go back to our function definition, this x squared y minus y cubed, and we're going to put in an x plus delta x where the x was, and then all the places that the y was get replaced with y plus delta y. Then after that, we just have minus the function itself, okay? And so the algebra of this gets a little yucky, but y'all know how to expand out a quadratic, how to square something. That's not a problem. And the y plus delta y, we're just going to leave alone at first. The cube, you may not be able to do it in your head. You may have to take y plus delta y squared, and then multiply it by y plus delta y again. But when you do, it will turn into this y cubed plus 3y squared delta y plus 3y delta y squared plus delta y cubed. Whew. And here at the end, we're subtracting off the original function and make sure to distribute the minus. That way everything is going to cancel off as we need it to. So if we go ahead and multiply out everything that was appearing in this bit here, it gets to be a bit of a mess, but we end up getting, by multiplying by the x stuff by y, we get this part, and by multiplying it by delta y, we get this part, okay? And then we need to take and distribute the minus through on this y plus delta y cubed term. And so that gives you all this mess right here, okay? And remembering that we have the original function stuff getting subtracted off there at the bottom. So if you'll notice, you are getting x squared y canceled by the minus x squared y, and you're getting the minus y cubed canceled by the plus y cubed. Then all the terms that remain all have delta x's and delta y's, okay? And that was something that we found in our definition of the derivative. We had everything that didn't have a factor of either delta x or delta y, depending on what we were working on, was going to cancel out. So now we've got to go to the next page here, and I'm going to have to ask you to kind of trust me a little bit that I'm not going to cheat on this. Remember that f sub x was 2xy, and we need an f sub x times delta x. And if we look to see what we've got going on there, nothing else has just a delta x for a factor of it. If we look at stuff that has just a delta y, we have the x squared and the minus 3y squared, okay? So here on the next page, we're going to put that f sub x, and I drew something a little too thin here, I'm afraid. So, but we've got the f sub x times the delta x, and we've got the f sub y times the delta y. Then this thing that I refer to as epsilon 1 and epsilon 2, those are like your recycle bins. You kind of have to go through and sort what you're doing with them in order to see what's going on. If you look back to the previous page, I'm not going to, but if you did, you would see that you have a y delta x squared. And so I took y delta x and put it in the epsilon 1, and a delta x that remained as a factor, I put it out here at the end. Essentially, this means that you had a factor of at least two things that were going to 0. Then another term that we have is delta x squared delta y. And so I put that in there with one of the delta x's on the end. And then there's also somewhere else in it a 2x delta y delta x. And so I sorted it into that part. And one of the things that you need to realize is that you have some choices here, okay? For the epsilon 2, I just went ahead and put the minus 3y delta y squared with the factor of one of the delta y's put out at the end. And the minus delta y cubed, I put two of the factors here and the one at the end. So please realize on this that since this term here and this term here had both a delta x and a delta y, these could have been dumped into the epsilon 1 tray instead of dumping into the epsilon 2 tray. Totally a choice on my part. It also means that the solution that you have is not going to be absolutely unique. When I come through and grade this, and you've done one of these, you may have a different answer than your buddy does, and you can still both be right, okay? So now that we've identified what epsilon 1 and epsilon 2 are, and we see that even after factoring out the delta x, that we're left with another factor of delta x or delta y, then that tells us that our epsilon 1 is going to go to 0. And by the same token, because we've got a factor of delta y beyond the first one we factored out going into the epsilon 2, then epsilon 2 is going to go to 0. And so when you know that you have both of those being true, that tells you that your f is differentiable at any point x, y that you wanted to work with, okay? So that's how you show something's differentiable. It is a little bit bulky, I realize that. If we were working this out on a piece of paper, you could probably fit it all on one page of paper, but because I'm trying to write it big enough that you can see it on a computer screen, it may not be so easy to get onto one page. Here's the other sort of problem that you'll run into, figuring out a tangent plane. So a tangent plane to a differentiable function, any function f of x, y that is differentiable, at a given point, and we always write the sub-zeros there to mean that it's a fixed number, okay? I probably should have just written ABC or something, but I was afraid that that might give the impression that we were introducing even more variables here. No, x naught, y naught, z naught is just you've chosen values for x and y and z, okay? But the formula that you've got for it will have a z minus z naught on this side of the equation, and the f sub x, x minus x naught on the right side, along with the f sub y, y minus y naught. Now, look back at your definition of differentiability. Z minus z naught is the f of x plus delta x, y plus delta y, minus f of x, y. The f sub x times x minus x naught is f sub x times delta x. And the f sub y times y minus y naught is f sub y times delta y. So these really are all the same things as we saw in the previous problem, just done a little bit differently, right? So then here, if we've got a problem that says, and maybe I'll change it so that it says that this is an example, find the tangent plane to f of x, y equals x squared y plus y cubed. That's almost exactly the same things we had before. I changed it a little bit just so the numbers would be nicer. Last time it didn't matter because it was all algebra and it was all going to be nasty. But now I just wanted the numbers to work out a little bit better. So in doing this, we're asked to find a tangent plane, calculate f sub x, 2xy, boom, done. Then plug in your point that you're going to work with here. And you find out that f sub x at the point 1, -1 is -2. Then we come back here and do our f sub y, okay? And the f sub y, oops, sorry. The f sub y that we're doing here just turns out to be x squared plus 3y squared. So once you've got that, then you can plug your 1, -1 into the f sub y, and it turns out that you get 4 out of it. All right. So keep those in mind as we go along here, because at this point, all we have to do is to plug into the formula we had. If you need to go back and check, the point -2 came from plugging 1, -1 into this function f of xy. But that means that you've got this z minus a -2 is equal to -2 times x minus 1, because the x naught was 1, and plus 4 times the y minus a -1, so y plus 1, okay? So if you're doing those, then the equation that you come to right here has z plus 2 being -2 times x minus 1 plus 4 times y plus 1. And that's okay for a solution. It is following the exact format of what you're asked to do, but it's a little bit clunky. A little bit better than that would be if you transferred all of your x and y stuff over to the left-hand side, and you have 2 times the quantity x minus 1 minus 4 times the quantity y plus 1. And if you'd like, you could think of it as plus 1 times z plus 2, okay? That's a little bit better. It fits a different format that will get discussed a little bit in your textbook at a later place in there. But probably the best way to handle it is to distribute the 2 and the 4 out, and then move all your constant over to the right-hand side. If you know a little bit about vectors, this means that the vector 2, -4, 1 is actually the normal vector to the plane at that point. If you don't know about vectors, don't worry about that so much. However, ask Don about vectors. I'm sure he'll talk to you quite a bit about them. We have broken things apart for the semester just a little bit differently than we used to, and so the vector stuff has come out of Calc 3 and gone into the vector calc class. So in any case, that's your examples of what we're looking at doing here. I don't have a whole bunch of examples or a whole bunch of problems for you to work, because this differentiability is just super cumbersome. It just takes a lot of working out. So what I'd like you to do is to make sure and work out at least an example or two. I don't remember how many's in the homework, of showing that something's differentiable. Get used to what we're doing with it, and you know, expect something like it when it comes exam time as well. But it has to not be super long. I don't feel too bad about asking you to do something that's super long for a homework, but you know, for a timed exam, it has to be relatively short. Okay. So anyway, though, do that for practice, get things turned in. Next thing we're going to be talking about is the chain rule, and I'll see you in class.